So what we are going to continue our detour into how we discussed Dirac equation. It's Lorentz covariance. Covariance means it will not differentiate between how we can uska derivative in whichever direction it may be there. So you can say we have to see the covariant for of Dirac equation. So there are a set of identities which we are going to see how we can incorporate the notions of Lorentz invariance in the Dirac equation. So the point is, for example, if you remember in your course in relativity, how we can relate two space-time points in space, but modulo there is Lorentz. So there is an upper bound of velocity of light. Things cannot travel greater than the speed of light, or the set of equations they may transform according to the Lorentz transformation with a factor of 1 by root of 1 minus v square by c square. So if you want to have, for example, if there are two observers, O and O prime or O dash, जो भी आप कहना चाहेंगे, ठीक है? So you have to see rule, you have to see construct rule which relates ordinates x mu with which observer O describes the event x mu prime used by observer O prime to describe the same vector. So you have to see what you have to see. How observer O, for example, describes the event, and which is being seen by the. But you see, the observer here, this it goes from since it's special theory of relativity, mu goes from 0, 1, 2, and so here this is CT. This is we normally write it in terms of time coordinates. So you see, so it can be x, space coordinates, y or z, or if you want, or x1, x2, x3. So you have to relate how we can relate two space-time points for observer in O vis-a-vis observer O2 dash. So this is the thing. And if you want to write the same in the metric language, what we are going to see is that the Lorentz transformation between two sets of coordinates क्या है x mu prime is equal to so it will be A prime mu x1. So you see, you can write. So if you want to just see here, so you can have x mu prime is to be related by x mu. So these are two space-time coordinates in frame observer O prime vis-a-vis observer O. But you can see it can be mediated by this tensor or this matrices. So you can take it as if, for example, mu will contract, mu goes to this. You can see this. If it's x mu, it's x mu. Sorry. So you can say, so mu can contract with mu. You can get a mu prime is related to A nu. So this is how you can relate two space-time points via some transformation. This is a sort of matrix transformation, or you can write it like this. And if we, for example, जो basic हमारे पास जो Lorentz equation, Lorentz invariant transformation in the transformation in a proper time interval can be, so d square will be g mu mu dx mu dx. Fine. You can contract one of them. It will be nu, and again it will be, so it can, so it's g mu nu can be related with eta mu nu also in some sense. It's general g mu nu. Eta mu nu means a flat space time which has either 0 1 1 1 or 1 1
minus 1 1 1
0 1, so whatever that is. Or you can further write it if you want to write it like this. Here also mu goes from 0 1 2 3, and this also goes from. So if you see why we have put one upside down, so once you multiply it 0 1 2 3, so it will be like this. It will come out to be like this. Fine. So it will come out like this. You can see you do this exercise of अपनी जगह इसको करो 0 1 2 3. So if you just number the previous equations are to be numbered. The previous equations are to be numbered like. Like 1, 2, and you can see the coefficients A mu mu and A mu sigma can be written as you can write it as mu will contract mu, it will be delta mu sigma.
Yes, sir.
Now there are two sort of transformations. One is known as proper Lorentz transformation, another is the improper Lorentz transformation. Proper Lorentz transformation में you जो determine है right hand side में, it can be plus minus 1. So if you take plus 1, so minus 1 का factor आने से, how we define that space? We define that space sometimes in the Minkowski space में हम define करते हैं. So that's another discussion. If the transformation between two units, it's an improper Lorentz transformation. So that's a so where the determinant is not equivalent to plus 1, it might be minus 1. So if you take a determinant which is determinant of A, this will be plus 1, and which is proper Lorentz transformation. A किसका? A इसका. This. So it may be the transformation along any of the space directions. It's transformation along any space direction, any space directions, and they may be infinitesimal transformations. While in case of improper Lorentz transformations, they may be rotations as well as what I should say, they are discrete transformations in space and time. So इतना थोड़ा फर्क है in this thing. So if there are discrete how we can relate proper Lorentz transformation with the improper Lorentz transformation. Leave it that way, such that we see in improper Lorentz transformation root e to by minus 1. This is another task. Now we are coming back to our Dirac equation. Lorentz invariation in case of Dirac, if you remember, we can write mu as m square s square based on previous chapter. Where, and if we write remember equation 1.13 in the previous law. हमारे पास जो इक्वेशन 1.13 है केवल I by h d psi by dt h c by d alpha d psi 1 by d xi plus alpha 2 d psi by so on and so forth plus beta mc square equal to xi. So if you remember this equation, and we can use gamma naught को हम बीटा के साथ यूज करेंगे, and gamma I can be replaced beta alpha I, such that I goes to 1 to 3. So if you use this transformation in some sense, and gammas here alpha जो है हमारे पास, which we normally represent as different matrices, है ना, gamma 1, gamma 2, gamma 3, gamma 0. They are in terms of poly matrices, but these are 4 cross 4 matrices satisfying equilibrium algebra. अब इसमें ये है कि if you want to use this notation, gamma को in terms of we are going to write in terms of alphas like this. So if you do this notation this way, so you can restate it in terms of gammas. अगर betas को in terms of gammas लिखें हम, betas means these betas. These alphas को in terms of these alphas को in terms of betas लिखें, और betas को in terms of gammas लिखें, then it will come out to be alpha h gamma 0. Now again we are using Clifford algebra here. You can just आप इसका ये कर सकते हैं, you can whatever just show it. Where gamma I can be and gamma 0 is equal to. Now we can now here one thing is that we can use इसको कहते हैं Feynman's dagger or Feynman's slash notation. Yeah, Feynman's dagger. So whatever. So notationally we are going to see how we can write this transformation in terms of. So if we want to write, if we write a mu a prime as gamma mu a mu, here g mu u आप इसको ऐसे लिख सकते हैं. So you are writing this a prime so this contracts with this. You will get a prime can be related with a. So in the same way, mu will contract, mu contract. So a prime will be related with this via this notation. Where mu can be 0, 1, 2, 3. These are space-time coordinates. अब ये so we are doing the same thing. We are writing the same thing. The only thing is that we are going to introduce this slash notation. इसको Feynman notation भी कहते हैं. So if you write a prime like this, then further. So now if you want to write it, अब इसमें आप क्या काम करोगे? पहले करोगे gamma 0, gamma 1, gamma 2. So we'll just classify time coordinate gamma 0 अलग रखेंगे 1, 2, 3 से. So you can write further. इसको हम ऐसे भी लिख सकते हैं ना, gamma 0 minus gamma a. Where it can be gamma 1 a1, gamma 2 a2, gamma 3 a3. और if you want, if आप थोड़ा सा notation करोगे, ये प्लस आएगा, ये माइनस आएगा, ये माइनस आएगा, ये प्लस आएगा. It doesn't matter. So if you write it this way, or particular, if you write your earlier classes, gradient notation in del, it can be written as लिख सकते हैं इसको ऐसे. So this is time coordinate. These are है ना, यहाँ पर ये ऐसे gamma dot divided by x. It's like you have written it like this. These are space coordinates. This is
time.
And we know that or gamma plus Dirac equation for in terms of gamma, it can be or you can write it like this. Further, if you want to write P mu as, we can write this equation as dNx by dx. We can write it in terms of P mu. Or we can write it in and if you remember, P mu को हमने ऐसे, when we introduced gauge potentials, we wrote P mu as so this equation fine. So this is in the preliminary way we can write notation of Dirac. Okay, in that sense. So now the next thing is there is a particular proof of covariance. How we can show the covariance of the Dirac equation using the notation which we have introduced here. The way in terms of Feynman's this slash notation. Okay. So the proof is a bit थोड़ा इसका longer है. Okay. So we are going to see how we can introduce slash notation to just show the proof of covariance. Proof of covariance. We have to show the proof of covariance in an algebraic way. So it will take maybe a larger class. Okay. So tomorrow we'll do the proof of covariance. Okay, in some regression. Okay.